Thank you, Ronald, for the presentation. This presentation is titled Formal Verification of the Rainbow Security Model. So we will cover the security aspects of the verification of the protocols. And in particular, in this presentation, we'll talk about security through formal verification. So what is in general security assessment, what is formal verification, and why is it needed for security protocol? Then we will take a look at the available tools used for formal verification. And finally, I will show you some results of the Rainbow Protocol verification. Let's start with a security assessment. So why is formal verification important nowadays? As we all know, all the protocols can have vulnerabilities and weaknesses that can be exploited by attackers, and these can cause failures and incidents on our system and a violation of the security policies of our system. According to some studies, the cost to fix this vulnerability increase while proceeding with the development of the system. So it is necessary to there is the need to detect this vulnerability at the early stage. So, for example, during the design of the system. There are two techniques that can be applied when analyzing the security of a system that are static analysis and dynamic analysis. Static analysis, as the word itself suggests, means analyzing the security of a system in a statical way. For example, checking the code or the documentation, so without having the concrete real system running. While dynamic analysis instead consists on testing a running instance of the concrete system, for example, through penetration testing. Here in this presentation, we mainly focus on static analysis and in particular formal verification, that is a branch of static analysis. And static analysis is important because even if it is more expensive, because it is very difficult to automate, it can be done in the early phase of the development cycle because it doesn't require the final real concrete system running. So let's now come to the definition of what is formal verification. As mentioned before, formal verification is static analysis of a system formal model. So that means analyzing the security of a system by building an abstract model of it. The entire process consists of two phases that are the formal specification, that is starting from a system, build a formal, mathematically rigorous model of it. The model describing the system must be unambiguous, so without multiple interpretation, consistent, so without internal contradiction, and complete. That means that all the relevant information of the system should be present also inside the model. Here are some examples of models describing a system that are, for example, the state machine or logic formulas. For example, the last one is a particular logic formula called on close. And while the second phase instead is called formal verification, that consists on verifying if a system model satisfies some formal property that mainly are its security requirements. So there is a verifier, an automatic verifier that takes in input the system formal model built in the previous phase, some properties to be checked, and then the verifier return correct plus eventually a proof of correctness if the property are satisfied, or not correct plus eventually an attack trace if the property are not satisfied. So why is formal verification needed for security protocol? Nowadays, designing and implementing security protocol is an error-prone task, and several flaws are constantly being found even after a year from the deployment of the protocol. So there is the need for formal methods that check in an automatic way and in a rigorous way if our protocols and system contain vulnerabilities. So we need formal methods to increase the confidence in the security of the protocol. Notice that being static analysis, it doesn't fully guarantee that the protocols are vulnerability free, but it still gives us a very high assurance. And this is the reason why um, we decided to apply the formal verification to the Rainbow protocols. Um, there are two possible modeling approaches used to build the model of a system that are symbolic models and computational models. Symbolic models are high-level models that uses abstract data types that are called symbols. And here we can say that the main difference with the other approach is that with symbolic model, we consider cryptographic primitives as black boxes. That means that we don't specifically model the cryptographic primitives, so no internal details of the primitives are modeled, but we consider them trusted by assumption. And so all the vulnerabilities related to the cryptographic primitives are not detected by symbolic models. For example, if in our system we use the DS encryption protocol, its vulnerability are not found by the verifier. Here, with the symbolic models, protocols are modeled following the Dolev-Yao model. That means that honest actors behave according to the protocol, according to the model, while there is no need to model the attacker that can behave in any way. In particular, it can build, read, insert, delete, substitute messages. It can build new messages from its current knowledge, or it can, but it cannot, it can do cryptographic operations, but it cannot guess secrets. So for the verification, no brute force attacks are considered. And also it cannot guess only partial knowledge of a secret. So, or get the whole secret or nothing. Here we don't speak very much about computational model because even if they are more precise models, it is very difficult to build automatic verification tools that use computational model for the verification, and nowadays they are not so widely used. Also in Rainbow we implemented the symbolic modeling. Here for the computational model, I just want to say that both the protocols, the attacker and cryptographic primitives can be modeled as algorithms that are polynomial time algorithms. And here, nothing is impossible, but some operation can be done only with non-negligible probability. For example, a reverse function is an operation that can be done with negligible probability. And here the objective is to prove that an attacker can reach a goal in polynomial time with non-negligible probability. But as I said before, here in this presentation, we mainly focus on symbolic models that are the one widely used today for the verification of the protocols. In particular, we will see some tools used for symbolic models. The two most famous are ProofReef and Tamarin. ProofReef was developed by Bruno Blanchet, and it takes in input protocols written in the applied P calculus, that is a specific language of the tool. And ProofReef was developed in 2002. So nowadays it is very notorious. It has been widely used, and so it is a lot of stable, very stable. ProofReef is sound but not complete. That means that sometimes it can detect false attacks, but if he find the correctness proof for a property, then this property is guaranteed to hold. This means it is sound. Unfortunately, ProofReef may have problems managing protocols with global state. And in our case, in Rainbow, it is a big limitation because of the state introduced by the TPM, in particular by its PCRs, as Heini and Raphael said before. And so there could be limitation using ProofReef, but fortunately nowadays there are possible extension of ProofReef that allow us to handle also the state, and these are, for example, StatVerif or GSVerif, that stands for Global State Verif. While the other tool also is Tamarin. Here is the list of its authors, and also Tamarin has its own syntax based on lemmas, and nowadays it is very notorious and widely used. For example, if I'm not wrong, Tamarin has been used to verify the TLS protocol. And so it is very famous and stable, of course. And an interesting thing of Tamarin is that it provides an interactive modes with the user. That is, if the tool is not able to find the correctness proof for a property, then the user can directly interact with the tool, guiding the proof. While Tamarin can manage protocol with state. Okay, in Rainbow, we decided to verify the protocols using ProofReef, but we plan for the future also to verify them with Tamarin to have a greater assurance of their correctness. So let's now see how ProofReef works. ProofReef, as I said before, takes in input the model of the system written in a particular language, that is the applied p-calculus, either typed or untyped. And then it takes in input also a series of security properties expressed as queries. Then he translates both the system model and the queries into on clauses, that is logic programming. And try to find a resolution to the problem, that is to demonstrate that the security properties hold for the specific system model. ProofReef can return different outputs. For example, it can return true if the property is true, so the property holds. And so if he has found the correctness proof for a property, return true, but the proof is not released, it is kept internal to the tool. Or ProofReef can return property cannot be proved, and in this case, ProofReef starts a state exploration to find for possible attacks. If a potential attack is found, and if it is not, of course, a false attack, then we are sure that the property doesn't hold. And the ProofReef returns as output also the attack trace. While if no attacks are found, we cannot know nothing about the property. In fact, the state exploration is not exhaustive, and so even if ProofReef has not found an attack, a real attack may still exist. ProofReef can also not terminate, and also in this case we cannot know nothing about the property. So these are the three outputs that ProofReef can return. So let's now see the Rainbow protocol verification. I will first give you a general overview of the protocols implemented in ProofReef and which are the one target for the verification. That are the Rainbow zero-touch configuration that is used for secure enrollment of a node into the fog environment and for its integrity verification. In fact, as Raphael said before, when a node wants to enter into the network, into the fog environment, must give confidence of its configuration integrity, and it is done through the attestation by quote and attestation by proof protocol. The attestation by quote is used to demonstrate the configuration integrity to a remote orchestrator, while attestation by proof implements a sort of decentralized integrity verification when a node wants to know the configuration integrity of another node without passing through the orchestrator. Both these two protocols, attestation by quote and by proof, were overcome with an enhanced version of them, that is the reinforced zero-touch configuration. Other protocols target for the verification in Rainbow are the direct anonymous attestation protocol that is used for authenticating nodes in a privacy-preserving and accountable way, and the anonymous secure channel establishment protocol used as an alternative to TLS for privacy preserving, and used to build so secure channel between the nodes that want to communicate. So before running, the two nodes have to establish a secure channel before running one of the two described protocols. We have finished the verification of the attestation by quote and the attestation by proof. And we are currently working on the verification of the reinforced zero-touch configuration, that is the enhanced version. In particular, in this presentation, I will show you the results of the verification of the attestation by quote, because it is the easier protocol, so because it is easy to explain and understand also. But before going to the definition of the protocol, I will first give you a general overview of the attestation by quote protocol. How does it work? How it work? So, as Heine said before, the attestation by quote is used to verify the integrity, the configuration integrity of a node. The configuration values for a node are contained inside its TPM, specifically inside some registers of the TPM that are the PCRs. And the orchestrator, the remote entity, maintains for each fog node a list of PCR that are virtual PCR that reflects which are the expected value for the PCR of the node. So if the virtual PCR and the PCR of the node are aligned, then the node is considered trusted. If they are not aligned, the node is not considered trusted, and because probably it has been hacked. And whenever the orchestrator wants to know the configuration integrity of a node, he starts the attestation by quote protocol. He first precomputes which are the expected value for the PCR of the node, reading its virtual PCR, and then he sends the request to the node. The fog node forwards the request to its TPM that reads the PCR, compute a digest, and sign the response message. Then it forwards the response to the orchestrator that checks if the signature is correct and if the VPCR and if the PCR contain the same values of the virtual PCR. If the two values are equal, then the node is considered trusted. Sometimes it can happen that the orchestrator wants to update the security policies, for example, when new vulnerabilities are found, and this implies a modification of the set of the configuration to be checked. So, for example, adding a new configuration file to check. And so a policy update protocol is started. The orchestrator precomputes which are the implication of this modification, accumulating a new value into its PCRs, and then send the policy update protocol to the fog node. The fog node invokes the tracer, that is an external agent in charge of reading the configuration file of the node. The tracer reads the configuration file, return the value that is then accumulated inside the PCRs. Now, if the configuration file is correct, so the fog node is under a correct configuration, PCR and virtual PCR are again aligned and the node is considered trusted. We have extracted a series of requirements to be verified and checked with the formal verification. And these properties are configuration correctness, that states that a node must adhere to the latest attestation policy issued by the orchestrator. Trustworthiness, that states that it must be possible at all times for the orchestrator to determine the trustworthiness of a node, for example, through the attestation by code protocol. Then the immutability property that say that the tracer reading the configuration file must always return the correct read value. And then liveness and control invocation that state that the node must reply to the request within a specified time. We built a formal verification of this protocol and these properties with ProofReef, and some attack trace have been found. But before analyzing them, I just want to say that no encryption or authentication mechanisms were used while verifying this protocol. So, for example, some attack traces are the direct consequences of missing authentication of messages, and all these attack traces have been found with ProofReef. Yes, ProofReef was able to find all these attack traces. Here I drew a simplified scheme of the attack traces, because the direct output of ProofReef probably is not immediate to understand. So I just wanted to draw a simplified scheme of the attack traces that are the following. For example, the first attack trace is called fake policy update request. And here, the policy update protocol is not started by the real orchestrator, but it is started by an attacker that send the policy update request to the fog node. The fog node invokes the tracer, read the configuration file, and accumulated inside the PCR a new value. But because of the process was not started by the orchestrator, so the VPCR of the orchestrator were not accumulated, now PCRs and virtual PCR are not aligned, and this leads to a denial of service attack. So denial of service attack because PCRs and virtual PCRs are not aligned, so the node is considered untrusted. Here the solution is simple authenticating the policy update requests. The second attack trace, called the unsecured tracer channel, is the following. Here, the policy update protocol is correctly started by the orchestrator. So the orchestrator sends the policy update requests. The fog node invokes the tracer to read the configuration file. The tracer reads the configuration file and returns the read value, but the correct read value is intercepted by an attacker and it is changed into a different values. So also in this case, inside the PCRs is accumulated a value that is not the expected one, but it is a value modified by the attacker. And also in this case, this leads to a denial of service attack because, again, PCRs and virtual PCRs are not aligned, so the node is considered untrusted. And this is a violation, for example, of the immutability property. If we come back to the description of the property, immutability property was the one describing that, stating that the tracer reading the configuration file must always return the correct read value. And yes, in this case, the tracer returned the correct value, so reads correctly the configuration file, but the return value was modified by the attacker, was intercepted and modified by the attacker. So here the solution is to build a secure channel between the tracer and the TPM. The third attack trace is called hacked node. And again, here the policy update protocol is started correctly by the orchestrator. But in this case, the node has been hacked by an attacker. So there is an attacker that has hacked the fork node. And when the tracer is invoked to read the configuration file, this file, the tracer reading the configuration file reports an unexpected measure because the configuration file is in an incorrect state. But in this case, also, again, the attacker intercept the value returned by the tracer and change this unexpected measure into the expected one. So at the end, into the PCR is accumulated a value that is the real expected one and not the one reported by the tracer. Here, the consequences are more catastrophic because the node is considered trusted even if it has been hacked. But again, there is a simple solution here that is to secure the channel between the tracer and the TPM. That is the same solution for the previous attack trace. And these attacks is a violation of the configuration correctness property. The last attack trace instead is the following. And also in this case, it is a direct consequence of a missing authentication of a node, because also in this case, the attestation by code protocol was not started by the correct, by the real orchestrator, but by an attacker. So also in this case, this leads to a denial of service when the fork node is flooded by attestation by quote request sent by an attacker. And in particular, here the fork node consumes a lot of energy, lot of resources, doing expensive cryptographic operation because it has to sign each response message. So also in this case, there is a denial of service attack. And yes, again, the solution is the authentication of the attestation requests. So for the conclusion, we have verified, we have detected a series of logical flows attacks with ProofReef, and so ProofReef increased the quality of the security analysis. And in particular, we've seen the results of the verification of the attestation by quote protocol. I just want to say that all these attack traces had been already considered by the designer of the protocols, of the Rainbow protocols, before the formal verification. So the formal verification was just a confirmation of what was expected, and also what was overcome with the enhanced attestation protocol, so with the enhanced version of the attestation protocol. And as future work, we plan to continue with the verification of the other Rainbow protocols, so verify all Rainbow protocols, also using Tamarin when ProofReef fails. For example, I said before, managing state, ProofReef can have problems. So we plan to try to use Tamarin also as well. So, okay, thank you for your attention. I think it is all.
Thank you, Simone. Also here, do we have questions right now?
I can maybe just ask a very quick question here. So you ended by saying that you consider Tamarin because of this global state.
Yes.
Is there any specific reason why this is needed, or what is the practical limitation of why this is needed?
Yes, yes. In general, I can say that ProofReef sometimes is not very good at verifying protocols with global state, and because it doesn't offer direct support for managing global states. And this is, of course, a big limitation in the case of the Rainbow protocols because of the state introduced by the TPM. There are some tricks that can be used to solve the problem. For example, modeling the state variables as private channels, but without going too much into details of the ProofReef syntax. I just want to say that there are some approximation or some ways to solve this problem with the state. But this approximation also can lead to the detection of false attacks. So after the end of the verification, the user has to manually correct the results reported by ProofReef in order to filter and discard the false attacks found because of this approximation. And so, yes, the global state is a big limitation with ProofReef. And here for the attestation by quote protocols, we were able to overcome this limitation by filtering the results and discarding the false attacks found, all the false attacks found. And we also used for the verification of the attestation quote by quote protocol StatVerif, that is an extension of ProofReef. I mentioned it here. Yes, there is a ProofReef, StatVerif, sorry, that is a possible extension of ProofReef to handle global state. For example, it extends the ProofReef syntax by adding a variable that is SL that can contain and overwrite a state. So there is a variable that can be written more times, and this allows the modeling of the global state. And but with StatVerif, we verify the attestation by quote protocol, and the analysis terminated correctly. But unfortunately, for the enhanced version of the attestation the enhanced version of the attestation protocol, StatVerif was not able to conclude the verification, probably because the enhanced version is a complex protocol where multiple variable states are introduced, and also where, for example, some TPM commands can be executed only under certain specific value inside the PCRs. So it is a more complex protocol, and StatVerif probably is saturated and was not able to complete the verification. So for this, we also decided to consider GSVerif as an alternative to consider this limitation and to check to verify this protocol. Of course, as you suggested in the question, Tamarin is a real alternative to ProofReef because it can manage stateful protocols. So Tamarin doesn't have this limitation for global state.
All right, great.
Okay, I hope to have been clear enough.
Perfectly clear. Perfectly clear.
Okay, thank you.
Very good. Thank you.